As already announced, I'm going to talk about surrogate reactions, which I consider to be doorways to cross sections for unstable isotopes. And I'll get back to that in a little bit later. So this is a method that I have been working on with a number of my colleagues at Livermore National Lab. It's a combination of theory and experiment that we're using in order to get to cross sections that cannot be measured directly, but that are important for us and for many other people. Nuclear data, and in particular nuclear reaction cross sections, are critical ingredients for the computer simulations that are being performed in both applied systems and also nuclear astrophysics. For example, for nuclear power plants, we need simulations to safely engineer the power plants without wasting money for over-engineering it. Simulations of astrophysical phenomena are the only way that we can use to interpret the signals that we can get from space via the telescopes that are out there, via gravitational wave detectors, or even via grains that are included in meteorites that hit the Earth. In order to interpret those, we need to run these simulations, and we need to have nuclear data input. We've made over the years, we've made a lot of progress in understanding stellar evolution and element synthesis, but there's still some big questions that remain to be resolved. In particular, the detailed mechanisms and the locations of where the heavy elements are made is something that we would really like to know more about. And so in order to better model the relative importance of neutron star mergers and other potential sites for the R process, we need cross sections for unstable isotopes. Similarly, for understanding the conditions for the slow neutron capture process. And then there are, as you see in this chart on the left, there are other processes that we would like to understand. The I process, and we would like to understand how the P nuclei are made. For these processes, we need to have better knowledge of proton-induced as well as gamma-induced reactions. And one of the hallmark of all of these is that they're often not known for unstable nuclei. Now, all these, most of these reactions that I have mentioned just a moment ago are compound nuclear reactions. In such a reaction, what we have is we have a projectile, here little a, hitting a target nucleus, and it fuses. It produces a highly excited system that equilibrates, and then that system can decay in various possible ways: by particle evaporation, by fission, or by gamma emission. And if we want to have these reaction cross sections in our simulations, we need to evaluate these processes. For very low energies, we typically use an R matrix approach, and for higher energies, we have a statistical description that, in the Hauser-Feshbach formalism. The calculations typically are not predictive enough to be sufficiently accurate for our simulations that we would like to make. So we need experimental information to constrain the cross sections. The most critical part to constrain is the decay of the compound nucleus of this B star nucleus that are indicated here. The formation cross section tends to be known better, although we need to do some more work on optical models to improve this. But what do we do in order to constrain the decay better? One of the things that we can do if our nucleus A cannot be produced because it is too short-lived or too radioactive, we can use a surrogate reaction, which is indicated in the lower right-hand panel. The idea here is that we make this same compound nucleus B star by means of some kind of alternative reaction, a transfer reaction or an inelastic scattering reaction that uses a projectile target combination that we can deal with better experimentally. And then in this experiment, we observe the outgoing particles, in this case here, the B particle, that tells us where the nucleus, at what energy the nucleus B star is made. And in coincidence with that, we look at the decay of this nucleus. And from this information, we would like to infer enough about the decay of B star that we can then calculate a cross-section for the desired reaction. So this, of course, is not a new idea. In fact, it was used extensively in the 1970s to get a first estimate for a lot of cross-sections that people were interested in. And that idea then was followed for some years, and it was picked up again in the early 2000s by some of my colleagues at Livermore, but also by people in France and in Japan. And new fission cross-sections were measured using this method, and some new ideas emerged by using ratios, etc. The fission analysis almost all assumed that the cross-section simply factorize into a formation cross-section and a decay probability, and that worked pretty well for fission. And we did some sensitivity studies, and we understand why that works reasonably well. But then when you try to apply this to capture, what you get is what you see here on the right-hand panel. You see some benchmark experiments that were carried out where we knew the result that we should have gotten because there were direct measurements, like in the gadolinium case. That's in black, the black dots, with a line that was calculated to a curve that was calculated to go through this. And if you do a surrogate measurement, in this case it was inelastic proton scattering, and you analyze it the way people have analyzed fission, what you get is the result that you see in the yellow and blue dots. You're off by factors of 5, 6, 7, and the shape isn't right. So this does not work for fission. A group in France did similar test measurements and found the same. So that's the bottom panel that you can see. So we have understood this for many years. The point here is basically that when you make this compound nucleus by means of a transfer reaction or inelastic scattering, you do populate the spins in the nucleus differently. And that has actually, for capture, a tremendous effect. But it did take some while to solve the problem, and we have worked on this. We looked at PD reactions and DP reactions. So on the right-hand panel now, you can see the state of the art these days. We have gotten the zirconium and gamma cross-section out, and then there is a molybdenum cross-section that we got out from surrogate experiments. And I'll take you through how we do that in a little bit. And you have seen the molybdenum already because Andrei Radkevich talked about this a few weeks ago. So, as I said, I will take you through this, through the process of how we do that. Solving the problem requires using both direct and statistical reaction theory, and we also need some nuclear structure information. I will focus in this talk mostly on neutron capture and explain the theory approach that I used to get the N-gamma cross-section from the PD reaction and from the experimental data that my colleagues gave me. The zirconium case is a benchmark, and we then went ahead and did an application to a yttrium 87 and gamma. Yttrium 87 is short-lived. There's no direct data. I will only briefly mention the molybdenum because Andrew talked about this a few weeks ago. And then I will briefly highlight a few other ideas of what one can do with this surrogate approach. Okay, so again, I want to emphasize that we're dealing here with an indirect method to get a compound nuclear reaction. There are other reactions that are of interest, but the surrogate method focuses on compound reactions. In such a reaction, a nucleon undergoes here the desired reaction, let's say a neutron-induced reaction. The nucleon undergoes multiple interaction with a target nucleus and finally fuses to make this B star nucleus on the upper right-hand panel here. It's a relatively slow process, and the end effect is that we have an equilibrated compound nucleus that lives very long. And this has been known for a long time, as the pictures in the upper left-hand panel here show. Early experiments demonstrated that there are EV-wide resonances formed in low-energy neutron reactions, for example. And this compound nucleus lives for a long time. And for neutron capture, this is what this looks like. And in the picture, what we see is the neutron capture cross-section for a number of isotopes for which there's direct data as a function of neutron energy. We see the isolated resonances at the lower energies, and then as we move up in energy, the resonances get wider and wider, they overlap, and finally in the calculation they're being replaced by some average. So the curves that you see at the higher energies are averages. In the lower energy regime, you need to have an R matrix approach, and you need to fit that to data if you have data. For the higher energies, we can use the Hauser-Feshbach formalism, and I've indicated what goes into that formalism in the equation below. The cross-section for this higher energy regime has this form shown there, and that first T, the transmission coefficient that sits on the top of the fraction, the T alpha LS, is the transmission that describes the probability for forming for the projectile to fuse with the target. And then the other transmission coefficient describes the probability for whatever you're interested in to come out. And we're interested in the gamma to come out. So that is the gamma transmission coefficient, and it's related to the gamma ray strength function. The rho is the level density and the nucleus where you're ending up. And then in the denominator, you have analog transmission coefficients for all the competing channels. So that is again, that can be neutrons coming out again. It could be protons coming out. It could be fission. And you have to consider all the various channels in this case. And this is what causes the uncertainty in the calculation. You need a lot of structure information. You need the gamma ray strength functions, you need the level densities and the residual nuclei. And these are often not well enough known to be constrained. So how are we going to deal with that? So if you can do the experiment, and I should basically stop here for a moment. If you can do the experiment directly, if you have the target, you can get some data to fit your parameters. You can also get some information for the level density by just counting the neutron resonances. This gives you a point of reference at the separation energy. It gives you a constraint on the level density, and you can count the low-lying levels in the nucleus. That gives you another constraint on the level density. You can get average. You can get average radiation width by looking at the width of the resonances, and that gives you some information on the gamma ray strength function. And all of this will help you tie down your calculation for cross-section, for capture cross-section. Now, when you don't have that data because your nucleus is unstable and you can't carry out an experiment, then you have a problem. And this has been known for a while. And people in the astrophysics community are painfully aware of it. The example here shows some study from Mumpower et al. That illustrates that when you go along the chain of the tin isotopes and you get to unstable nuclei, so that's past the 82 here, the calculations have large uncertainties. So here the calculations are just some using different Hauser-Feshbach codes and using the default parameters, which is all you can do when you go off stability. You can try to use some systematics and some intelligent guessing, but you get large uncertainties. This is a log scale. So this is the problem when you try to do a calculation for capture reaction that involves unstable isotopes. So how do we in detail approach this when we do a surrogate reaction? So here on the top left hand, you see again the case of a compound nucleus. We want to do this first for a benchmark. So we chose neutron capture on zirconium-90. That cross-section is known. If you do neutron capture on zirconium-90, the compound nucleus is zirconium-91, and you make this compound nucleus above the neutron separation energy, which is in this nucleus 7.1 MeV. And the problem that we want to solve is we want to get some constraint for the cross section. I have rewritten the cross section in the green box on the upper right side there in a way that's a little simpler. The cross section is a product of a compound formation cross section in blue and the decay probability, the G's that are given in red, and it's a sum over all the spins and parities in the target nucleus. That G now is that fraction that we saw on one of the previous slides that we would like to constrain. It contains all the nuclear structure information, the level densities and the gamma ray strength functions and the competing channels, etc. So when we do a surrogate experiment, it looks like something like on the left-hand side. We start with a target projectile combination, such as protons on zirconium-92. We do, in this case, a PD reaction that makes a hole in the zirconium-92, and it gives us an excited state on zirconium-91. The experimentalists measure the outgoing deuteron that tells us exactly where we are energetically in the target nucleus. And in coincidence with this deuteron, they detect something that's characteristic of the channel that we're interested in. In this case, it's a gamma ray between some of the low-lying states in the zirconium-91 because they're fingerprints. And by keeping the beam energy fixed, but by looking at different energies of the outgoing particles and different angles, the experimentalists can basically scan through the nucleus from low energies to well above the neutron separation energy. And what they get is a coincidence probability, which is plotted in the lower right-hand panel. Shown is the coincidence, the probability of observing in coincidence the outgoing deuteron with a particular gamma ray. And this is shown here for excitation energy from about 6 MeV to 14 MeV. And you can see that the gamma ray probability is fairly flat. And as you cross the neutron separation energy, it drops down because now a neutron can come out and the probability of seeing that gamma ray drops. So from this information, we would like to get our constraint. So what I have done is I have written the observable in a way that I can deal with as a theorist. So this is the P that's written up right above. And what this is, it's a probability that the compound nucleus was formed in the surrogate reaction at a particular spin, at a particular energy with a particular spin and parity. That's this F. And then that it decayed in this channel to this gamma ray. That's the G. And the idea now is that I calculate the F. I use the P's that my experimental colleagues give me. And I do some decay modeling for the G, but I leave I vary my models and my parameters in this G until I achieve a fit. So I basically change my level density, my gamma ray strength function, and other structure information that goes in there until I reproduce what the experimentalists have given me. And that constrains my G. I can then subsequently recycle that in the upper equation and get a cross section. I then have a experimentally constrained cross section, which is what I want. So what's the problem with that? That should be pretty simple, right? We're dealing with a PD reaction and people have done PD reactions for a long time. The problem with the situation here is that we're not interested in the low-lying structure, such as starting from zirconium-92, doing PD and investigating the low-lying structure of zirconium-91. No, we want to go near and above the neutron separation energy, which is at 7.1 MeV here. And in the cases that we look at, they're all between 5 and 10 MeV. In order to make such a highly excited nucleus with a PD, you have to really remove nucleons from lower shells in the nucleus. And it is very difficult to get a microscopic description that tells us exactly where these orbitals are and how they're fragmented. So this is very, very, very tricky. And there's no off-the-shelf theory that you can pull out. But there's something else that we could use. What I used is the idea of the dispersive optical model. This is not exactly a theory calculation that I use, but I use some of the output that they get. So the dispersive optical model was introduced in the 80s by Maho and Sauter. And as far as I can tell, their idea was basically to connect the optical model at positive energy to the binding potential that describes bound state properties of a nucleus. And the most important part that they realized is that you have a dispersive contribution to this optical potential. The real part gets an extra contribution apart from what is called VHF here. It gets this additional contribution that comes from invoking the dispersion relation and using the imaginary part of the potential, which is indicated in the equation below with W. So the advantage of doing that is that you can carry out scattering experiments and determine a potential that's parametrized, but that uses this dispersion relation in order to get some idea about what the potential should look like for the bound states. Another advantage is that you get expression for for the spectral strength, that is the spectroscopic factor per unit energy interval. And this is the part that I've been after. So in the example that Maho and Sauter showed in one of their papers, which is shown here below, they looked at PD reaction on calcium-40 and also on D helium-3, hydrogen-3 reactions. And they found that the strength that the experiment sees agrees with their formulation. So this is what I have used here. I have used an existing dispersive optical potential by De La Roche et al. To get a handle on the whole structure for the deep holes in this case. And I have in the middle panel, you see the spectral functions for the various orbitals from which we can remove neutrons. And what you also get is you get the potential and the wave functions, the single particle wave functions that you then can use in the DWBA calculation. So I use that to do a DWBA calculation of neutron removal, one-step neutron removal from very deep holes in the zirconium nucleus. Now, what I've also plotted here on the very left-hand side, you see I tilted sideways the cross-section, the PD cross-section, or what the experimentalists refer to as the singles cross-section. And you see if you go to the neutron separation energy, you see it's all very smooth. And that should already be an indication that there is a problem if you just do one-step reactions. And it turns out, indeed, doing a one-step calculation does not reproduce the cross-section. It turns out that you get strong contributions from inelastic scattering and both the entrance and the exit channel. So the incoming proton can inelastically excite the zirconium-92 and then remove a neutron. We can also have the situation where the proton removes a neutron and the outgoing deuteron inelastically excites the remnant nucleus. And we have to take those contributions into account. So fortunately, there's a lot of data in the zirconium region. So I could look at the experimental data and basically adjust the coupling strength for the inelastic scattering calculation. Unfortunately, it turned out I needed to take into account a lot of states. What you see here on the right-hand panel are states, inelastically excited states in zirconium-90 for, I've plotted here 2+, 3-, 4+, 5-, all the way to 8+ states. And I had to use all of these kind of states in the calculations, so there are a lot of them. So instead of having a one-step calculation with about, I don't know, 10 cross-section, now one has to have all these two-step reactions, and one gets about 2,500 cross-sections if you add it all up. So of course I don't do a very large-scale coupled channels calculation where I do all the cross couplings, I have to use some approximations. I include both types of two-step reactions that I have mentioned, but I put some constraints on this. I don't have all the information for all the cross couplings. So I assume that there's no interference between the different paths to make this final nucleus. I have only forward coupling. Here I use a spectator approximation. But since I am interested in cross sections that produce a nucleus at very high excitation energy, where there's a high level density, I'm justified with these approximations. They're in the spirit of what people have been using for many years in pre-equilibrium studies. So one takeaway message from this here, though, is that when one includes all these two-step reactions, is that a much wider range of angular momentum become possible. We're not simply taking a neutron out and making a compound nucleus that has the same spin and parity as that hole that is left. We have all these couplings. So, and it turns out we can now have angular momenta to more than 10 h-bar. But when one calculates all these cross sections that I just mentioned, one gets what I've shown here. In the plot, you see the measurement in black. This is the PD cross section that makes the compound nucleus between 5 and 12 MeV. And the region of interest is right around the neutron separation energy. The blue dashed line is the one-step reactions only, and you see this is really not enough to reproduce the cross section. The two-step reactions are in red, and then the orange curve gives the result. So that's a reasonable reproduction. Oh, and I should mention, the cross sections are integrated over angles from 30 to 60 degrees, which is what the experiment had. So there's no normalization here. We see the two-step processes dominate, and we get a decent agreement between measurement and calculation. So that makes us pretty confident to move forward. What I can also do is I can look at all the cross sections that are associated with one final spin and parity, and I can add them up this way, and that will give me the relative population of the different spins and parities in the compound nucleus. And this is how that looks like. And I've plotted this in two different panels because otherwise it gets too busy. I have all the positive parity spins and the negative the positive parities on the left-hand side and the negative parities on the right-hand side. And so that is the spin distribution. And we see it varies very smoothly in that energy regime near the neutron separation energy. So what that gives me now is that F that I mentioned earlier that I need in order to move forward with the analysis. Again, my experimental colleagues give me the P, the coincidence probabilities. I calculate the F. I build a Hauser-Feschbach type decay model for the G, and I adjust the parameters in the G in order to reproduce the P's. And this is how that looks like. We see in those 5 panels different transitions in the nucleus zirconium-91. And we see the fit that we get. I use the Bayesian approach to do this. And the thick blue line gives the average, and the gray band gives the uncertainty that is associated with it. So this fit now has constrained the parameters in the decay model. And I can use that decay model now to calculate the zirconium-90 and gamma cross section. What I get is the thick blue line here and the gray uncertainty band. What I've also shown is some data and some calculations to compare to. And what I want to also emphasize here that I did not use any other constraints on the level density and the gamma ray strength function in my calculation that yielded this gray band. So you might ask, how good is this? It seems a little high and the uncertainty seems a little large, but it's the first result. And I want to point out a few things here. Number one is zirconium-90 is a closed shell nucleus. So what we see here is the resonances come up quite high in energy. So it is not a nucleus that for which a statistical regime where the Hauser-Feshbach applies sets in at very low energy. So I think that affects some of the uncertainties too. There's some direct data. In particular, people can focus on the red point, that's a little lower. It's unfortunately only in a conference proceeding, so there's not that much information on that experiment. The data that other curves that you see are calculations that use actually the D0 and the gamma. So there's a calculation by Forson in purple, and there's a Tyndall calculation, which is that hashed area. They both use D0 and gamma. And so we get agreement with those as well. But it turns out that if you actually look in more detail at this nucleus, it is not straightforward to get a reliable gamma, and I will show you that in a moment too. Okay, so some of the questions that come up. How good is that result? I said a few things about this. I would actually like some experimentalists to go out and remeasure the N gamma for zirconium-90. This is such an important nucleus, and I was a bit surprised that it wasn't known better. So one might want to know how much these two-step reaction actually influence the spin parity distribution. And how do I know that my calculations are correct? A question that sometimes comes up is, can you get a level density and gamma ray strength function? Can we apply this to an unstable nucleus? So let me run through some slides to give you some answers to this. We see here the spin distribution in the top left panel for just the one step, and below that for the one step plus the two step. And we see we get a much broader distribution and higher spins. And in the lower right-hand panel, we see the effect of that. If we only use one step, we can not reproduce the data. We do not get that shoulder in, that we see at the higher energies. But we do get that reproduced when we use two-step reactions as well. How do we know this is correct? So we have to do cross-checks. We can also calculate the transitions in the neighboring nucleus after a neutron comes out. And that's what I've done here. And so there were no more, I did not fit any more parameters here. I used the results from the previous fit, and I find I can reproduce gamma rays that our experimentalists observe very well. The shapes look very well, very nice. So that's gives us some confidence. Can we get level density and gamma ray strength functions? Yes, it's not the purpose to get the level density gamma ray strength function. We want to have this convolution that makes the capture cross section, but I did actually sit down and extract it, and it looks like it's in line with what direct measurements and alternative indirect measurements get. The uncertainties are large because you can sometimes compensate. The level density, making changes in the level density can be somewhat compensated by making changes in the gamma ray strength function, and we are looking at the convolution of those. But it can be done. So can it be applied to unstable nuclei? Yes, it can. We have, in the same experiment, my colleagues measured also yttrium-89 PD. Yttrium-89 is the only stable yttrium isotope. And from that, we had planned on getting the N-gamma cross-section for yttrium-87, which is unstable. The process is exactly the same. I did the calculations for the spin distribution, which you see in the right-hand panel. Again, they're very smooth. The separation energy here is at 9.3 MeV. But when you look at the panel for the singles cross-section, you see little bumps. These turn out to be isobaric analog states. Now, I did not have to do an extra calculation for the spin distribution that one gets for the isobaric analog states, because the spins of those are known, and we can get from the experiment the amount of enhancement that they bring in. So basically, every time the isobaric analog state here is populated, we get a little extra bump of that spin in the spin distribution, and I added that to that calculated spin distribution, and that makes a difference. Here is the fit to these gamma transitions that the experimentalists have measured, and it's the same as in the zirconium, but we now see little bumps up and little bumps down. They come from the isobaric analog states. Again, that shifts the spin distribution at that particular energy in a very specific way. And in fact, it shifts it down because these are spin 0 and spin 2 states. And that has an effect on these transitions. So that is, I see that as a check for the overall spin distribution, because when there is a change, the calculation reproduces what the data does. So that I was happy to see that. But again, I also want to point out we reproduce the fall off, which is relevant, the fall off at the neutron separation energy, which is relevant to determine all the parameters in the decay model. And then we can do can use that to get the capture cross section. And here in blue is our result. This is a bit higher than what some of the evaluations say, but those evaluations are only based on systematics. There's no D0, there's no gamma gamma available for this nucleus because it is unstable. And again, the surrogate method doesn't need that. Okay, cross checks. One cross check that one can think about is, of course, to look at the angular distribution of the surrogate reaction. This is something that has been done here in the bottom right-hand panel. I picked a few energies that were not at the isobaric analog states, and we see a very smooth change of the cross-section with angle, which is not what you see if you populate lower states. It would be nice to have more data at a wider angular range, but this is what we could get from the experiment. Okay, so I talked about PD. What about DP? Isn't that simpler? Well, I don't really have to say much about it. When you use the DP reaction, you might think you're much better off because you drop a neutron on the nucleus. But if you have listened to Jin Lei's talk, then you know breakup is a complicated reaction, and you have to think about many different contributions. So there has fortunately been a lot of work done recently. This was started in the 70s, caused a bunch of controversies, and was attacked by several different groups lately. And so we now have a formalism also for the DP reaction that 3 different groups can provide. I have worked with Gregory Potel and also Andrew Retkovich, who gave a talk about this a few weeks ago. Andrew analyzed data from a DP measurement, and we essentially proceeded in the same way. We used the spin distribution that Gregory calculated and the similar types of fits, and got the cross-section for molybdenum 95 and gamma, which is shown in the right-hand panel in the blue band. It agrees with the experimental, the direct measurements. This was a benchmark, so this nucleus is stable. So there was very good data there. So we were very pleased with this. And I want to leave you at this point with a caveat that it is essential to do this in conjunction with theory and taking into account the spin distribution. Because if you try to do what people have done in the past for fission, you get, again, cross-sections that are very far off. And we indicated that by those results in orange. This is similar to what I've shown you before for another case. Okay, so let me briefly just highlight some other opportunities that I see for using this method. There's, of course, a long wish list of things that we would like to do. So we would like to understand reactions on excited states. In stars, you could have situations where you thermally excite states, and you would want the cross sections on that. You want a bunch of other cross sections, P gamma, alpha gamma, PN. People in the data community would like N to N. we see great opportunities for experiments at radioactive beam facilities. And then in the end, we would like to go back to fission. So let me just give a few highlights. Reactions on excited states. So the yttrium case that I discussed is interesting because the yttrium isotopes have a host of isomers. And I actually sat down and calculated all kinds of N-gamma cross sections with my constraint model, constrained by the surrogate data. And what you see in the right-hand panel is the N-gamma cross section starting from the excited yttrium 87 state. There is an isomer at 380 keV. So you can do things like that. You might be interested in P-gamma reactions. Again, I went to the yttrium data, and since the compound nucleus that's being made is yttrium 88, that is also a surrogate for P-gamma on strontium 87. So I tried to extract a cross-section for that. Unfortunately, the data was in a range where there isn't much uncertainty. It would be nice to have had data that went back to higher energies to constrain the calculations at like 6, 7, or 8 MeV, because that's where there's more uncertainty here. But it's just a hint of a possibility, what could be done if you plan an experiment because you want a cross-section like that. N-to-N is an interesting case because in an N-to-N reaction, you have to go up to very high energies, up to, in this case, 30 MeV to make the compound nucleus, because you want to be able to evaporate 2 neutrons. It involves, so this whole reaction involves multiple compound nuclei. We have started looking at that. We've had an experiment where Nick Schelzer and collaborators used helium-3 inelastic scattering to excite zirconium-91 up to 30 MeV. And he observed helium-3 in coincidence with gamma rays and zirconium-91, zirconium-90, as well as zirconium-89. The first nucleus will give us a constraint on N-gamma, the second one on N prime, and the third one on N-to-N. So that's work that's underway. And inverse kinematics, I don't really want to say much about it because Andrew has talked about this, but my colleagues are exploring this. My experimental colleagues are exploring that at multiple facilities. We're very interested in looking at DP and inverse kinematics, but also in inelastic scattering inverse kinematics. Both of these are good options. Fission, the whole story of surrogate reactions started in the 70s with the desire to get fission cross sections. Fission is a very complex problem, and it's very difficult to describe theoretically. So if we can get some other information from experiments, that would be useful. There's been in the past, people have looked at trying to determine fission barriers, and Birger Bach has recently written a very nice conference proceeding where he summarized some of the older work that was done. People are now also looking at fission fragment mass distributions when the nucleus fissions after a transfer reaction or an inelastic scattering reaction. And of course, one can get NF cross sections, which is indicated in the lower right-hand panel. And I'm just flashing some other results of what has been done in the last 10 years or so in this area by both my colleagues and a group in France. And I see that work as something that is continuing. These results here all use a simpler version of the surrogate method where you do not take into account that there are differences in the spin distribution. And in many cases that works very well, but if you look very carefully at very low energies or at the onset of second chance fission, you see some discrepancies. So I think there's clearly room for improvements for using more theory. Okay, so I'm coming to the end of my presentation, and I talked about doorways. So where is the doorway in the surrogate reaction? It is the configuration that you're basically populating with your direct reaction. It's a simple state, but it's not an eigenstate of the B nucleus. It is spread over many states, and it is what makes the compound nucleus in the end. But it does help us think about the problem. In a surrogate reaction, you don't have the surrogate particle, the surrogate projectile being absorbed by the nucleus. You have really a fast reaction, a direct reaction that makes a doorway state. We can calculate the spin distribution of the doorway state, and that is the spin distribution of the compound nucleus, because the ejectile is in the detector or is on its way to the detector and is no longer interacting after this doorway state has been made. So that helps us actually get a little bit of a handle on this complicated process where we have direct reactions and compound reactions all interwoven in order to get to what we want. It's, in my opinion, it's a really interesting problem from the theory side, because we need reaction descriptions for both transfer and inelastic scattering processes. We need multi-step reactions. We need nuclear structure models for the states. And what kind of nuclear structure model we need depends on whether we do a pickup or a stripping or inelastic scattering reaction. So there's quite a variety of interesting problems here. We need to understand the spreading of the excited states, and I talked a little bit about the dispersive optical model, but there's a lot more work that could be done in this area. Okay, so and this is my takeaway messages. I hope I have shown you that we can make the surrogate method now work for capture reaction without using auxiliary quantities such as D0 and gamma gamma. What I think is a real strength of the method is that we can use different target projectile combinations and different reaction mechanisms to get to the same compound nucleus. So we can do cross checks and we can expand the reach of the method this way. I see interesting applications ahead in inverse kinematics at radioactive beam facilities. And I'm looking forward to also get more cross sections out for reactions other than N-gamma. I think I have made a case for the doorway states, and that it's very important to understand those. And I hope people realize that theory is actually essential in this endeavor, and that we need to work together between theory and experiment. So thank you.